Let's take a ride and visit an apiculturist. Hopefully, that word didn't scare you off and you know what it means. It's a person who keeps bees, or a beekeeper. If that word threw you off, then you're in for one heck of a surprise towards the end of this lesson as we explore a specific subset of white blood cells. The white blood cells I want to talk to you about are called B cells, and they are a type of white blood cell known as a lymphocyte. These cells are part of the adaptive immune system. This part of your immune system is involved in forming specific responses to a specific antigen, which are the recognizable parts of a virus, bacteria, and so on. I like to equate these B cells and their life cycle to that of the bees the apiculturist is raising. The bees are born in their home, the beehive. Before the bees are old enough to fly out of the hive, they have to mature there a little bit. And so it is that our B cells are also produced in a special place called the bone marrow, and they mature a bit there prior to leaving their home to do their job. We can also pretend that the bees in the beehive are born to collect nectar and pollen from only one very specific type of flower. However, until they go out into the real world and encounter this specific flower, they are called naive bees. Only after encountering the flower they were born to pollinate are they fully active members of their society. Likewise, the activation, so to speak, of B cells begins once they leave the bone marrow and travel to other organs in the body, such as the spleen and lymph nodes. On the way to, or once they reach a specific organ, naive B cells may encounter the very specific antigen or part of a foreign invader they were specifically born for. Once they encounter this antigen, their flower, so to speak, they become fully active and functional members of society. In addition to being born to recognize foreign invaders, B cells are also trained to avoid attacking our own body cells. This is critical, for if B cells were to produce little molecules called antibodies to attack anything they come across, we would die very quickly as our own immune system would attack and destroy our own body cells. It's akin to the bees and beehive. The last thing the bee colony needs is a bunch of bees being born that attack and kill all of their friends, family, and the beehive. It would spell disaster. Hence, the bees are trained to recognize their own kind from foreign invaders and only go after the foreign invaders. In any case, when our B cell encounters the specific antigen it was born for, it flies off to meet another type of lymphocyte called a helper T cell. The B cell then shows this specific antigen from a specific foreign invader to a helper T cell. If the helper T cell perceives this antigen to be something it was trained to recognize as being a danger, it signals the B cell to divide into something called a plasma cell. The plasma cell is a white blood cell that produces large amounts of antibodies. These antibodies are little proteins secreted by the plasma cells, which are produced specifically for one type of antigen. Once the antibodies are released into circulation, they go out to track down this antigen. If they recognize it, they will attach to whatever harbors this antigen, like the surface of a bacterium. This attachment may, in and of itself, cause a series of events that destroy the bacteria, or it may signal to other cells to come and destroy the invader. Another type of cell formed when a helper T cell signals a B cell to divide is called a memory cell. This is a long-lived white blood cell that can quickly form antibodies upon re-exposure to their specific antigen. In essence, if you got infected by a certain strain of flu you never had before, it'll take a while for the B cells to turn into plasma cells, which in turn take a while to produce antibodies, which are finally able to stop the virus. That's why you feel miserable for so long. However, if you are ever reinfected with the same strain of virus, you will now have memory cells at your disposal that formed after the initial infection. Since the memory cells are already there, they can begin to produce antibodies much more quickly. This can be done fast enough so that you don't even feel sick when reinfected by the same virus. Immunological memory, thanks to memory B cells, is what vaccination is all about. If you are exposed to an antigen from a vaccine, you will gain memory cells. Since the vaccine is a weaker version of the antigen, you typically don't get sick. When the real deal strikes your body, you'll already have memory cells on board for that specific pathogen, thereby preventing any serious signs of disease. However, not all of us are so lucky. There is a rare condition called X-linked agammaglobulinemia that spoils the party for some people. This is a genetic condition linked to the X chromosome, which does not allow for the maturation of B cells and therefore the development of plasma cells. The word agammaglobulinemia is just a gigantic and difficult word for the absence, A, of gamma globulins, or antibodies, from blood, emia. And you thought apiculturist was a tough word. I'm sure you can imagine the consequences of something like agammaglobulinemia. If there are no antibodies produced to fight an infection, death can occur rather quickly without treatment. This was by all means a very simplified version of what really occurs, but hopefully it gave you enough of an overview to appreciate how complex and beautiful this system of flower and pollen recognition is. Recall that B cells are a type of white blood cell known as a lymphocyte. Once triggered, a B cell can become a plasma cell, which is a white blood cell that produces large amounts of antibodies, or a memory cell, which is a long-lived white blood cell that can quickly form antibodies upon re-exposure to their specific antigen.